Um, some simple, depending on how you implement it. Sometimes you'll flush the symbol table. Sometimes you just doesn't just takes up some space. So it's just there. I think on your test it might be a different issue. Okay, so this is not what they see on the screen. Interesting. All right. Okay. Um, all right. I guess. Okay. I guess we'll get started. All right. Week 7 already. Um, so you got your test. Did anybody not get their test back? I think I got everybody. Okay, I didn't compute an average or anything, but I think most of you did really well. We can talk about the test a little bit before we move on to other things. Let me grab one so I have it. Okay, and due tonight, Lab 2, Part 1, and homework, Lab 2, Part 2 is next Monday. So let's talk a little bit about that. Homework, this is the last homework set on the LL1 stuff. That's due it's not a very long homework. You should be able to get that done. And that's why we're going to talk primarily tonight is the LL1 parser. And we're going to go through several examples in class. So you'll have it. Let me switch out classes so I can see the screen and you. If you don't have your lab 1 checked off yet, there are a number of you in Blackboard. You submitted it, but I haven't seen it yet. Let's do that tonight so you can I can grade and give you points for turning that in. I posted the project description already. There are 5 different options, and we'll talk more about that next week. So this week, I think we'll get through the LL1. So next week, we'll talk about a little bit more on what happens after you're done parsing. Okay, we are going to talk briefly about the bottom-up parser as well next week. So we're down to like 2 more weeks, and then that week we'll have another test during that week. So it's winding down. Remember, this is week 7. So Friday of this week is the last day to withdraw from any class. And when you withdraw from a class, it needs the instructor signature and the advisor signature. So if I'm not around or Fong is not around, you can email the form to us. So we get that signed because it has to be in by whenever the office closes on Friday. Saturday is too late, okay? So they can't withdraw. So if you're going to drop any class, make sure you get the signatures. And if you cannot find the instructor, email him or her and get an approval. Okay, that's the quickest way actually to get that. And then we can take care of the paperwork later. The registrar's office still like us to take care of the paperwork. Okay. If you are moving on to senior project, I know some of you are already in, but if you are moving on to senior project next year, the project proposal class has been moved to 10 o'clock on Saturdays instead of 2. Because it conflicts with the operating system lab. If you're planning to take writing 350, which unfortunately conflicts with the operating system lab and assembly lab, because there isn't an overlap there, writing 327 is an option. Okay, so writing 327 is an option. I just need to submit a form. I think I submitted like 7 forms today just to get that 327, 350 sorted out.
So 350 and 3/5 are equivalent, right?
Yes. It should be automatic. Unfortunately, it's not automatic, so I had to put in a form, but it is equivalent, yes.
Yeah, what is 327?
Advanced tech writing.
Okay.
350 is documentation.
I just saw in here you gave me an override for writing 350, but I'm seeing 327 this term.
Oh, you don't need 350 then. Oh, you don't need 350. No. If you already taken 327, you don't need 350.
I did talk to you last week. But
oh, okay. No, you don't need it. Okay. All right. So any other advising questions, please come see me. We'll sort it out. All right. Let's see. Okay, so very quickly on the test. Um, can we look at number 4? Let's look at number 4. And I have another slide. Come on, really? Okay, there you go. I posted this, so you should have it. Getting it on the screen. That is the right. Okay, there you go. Okay, let's take a look at number 4. I think most of you have problems with that. The left recursion removal. But the rest of the questions, I think they were fine. I think this is the one that gave you some trouble. So, again, the red doesn't show up on this projector. Got to figure out a color that will help. Okay, so I think this is the right question. Right. S is fine. Even though S goes to A, big A, little b, it's not recursive. Right? It is not ideal for top-down parser because I don't know what big A is until I go there. But also, look at S. S doesn't have any other rules, so you have to go there. So either it's going to parse, it's not going to parse. You don't have to backtrack from S. But it's not recursive, left recursive either. It doesn't have S going to S. Okay, so that's fine. Leave it alone. A has 3 rules. The AB is fine. The big T is fine. Same issue as previous one. It's not left recursive on itself. So I'm still getting work done. Probably not the most efficient way. If I could get rid of that first column, make it all tokens, that would make your parser work better. You probably discovered that too, as you were writing lab 2. TBC is fine. The only one's recursive is A going to A, because not only is not efficient, it's not getting out of endless recursion. I'm just keep going A, going to A, going to A, going to A. I don't really know when to stop. Okay, so that's the left recursive one. And how we handled that was we took the A, we move it to the end. We make it right recursive instead of left recursive. Well, we can't call it A anymore because that would change the whole grammar. So we call it X. So X going to CTX. So it's left, right recursive instead of left recursive. And you do need a lambda to end everything. So that takes care of A on the recursive one. And these non-recursive ones just gets the X tack on at the end. Right? So, and then same thing with the T. This one is not recursive. This one is. So move the T to the end. Can't call it X now because I've already used X. I'm going to call it Y. And then just tack on the Y to the little b. Right? That took care of the recursive part. And B is going to start. Then you're going to have B, C, 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 until I don't need any more. And for the lambda. Okay, so the same algorithm. Is confused because of the T here and the big A there. They're not left recursive. Okay, yes, they are non-terminals, but they're not left recursive. All right, so this next one, today's video is going to be interesting because it advances that one, but not my screen. Okay, so statement list, going to a single statement. That's a unit production. It's not a left recursion. Going to lambda, that's fine. Statement list, going to statement list. Left recursion. Okay, so again, what do? We take and move it, and we call it X. So if you take the statement list that was here and move it to the end, you have a semicolon, statement, and then X, lambda. And then everything else just gets an X at the end. So statement X, lambda X. Okay, so to make this correct, it should have the X there, not just the lambda. Okay.
But isn't it sort of equivalent?
It's, well, see, X also has the semicolon statement and the X,
But
right?
in the above statement, stat list can go straight to lambda.
Stat list could go straight to lambda. Okay, right now, so that has to jump hop over. Okay, so if I were to remove, notice X is a unit production. So how do I get rid of unit productions? I get rid of unit productions by taking whatever X is and put it in there. So I'm actually putting the lambda back in that way. Okay, but I'm also putting X in. Okay, so that was a little bit of difference there. Okay. All right. So we can take a look at, and everybody had all different answers. They were sort of all over the board. That's fine. So this is, all right. It's okay. All right. So number one, the unit productions. Of course, the number one, the big B and big C are unit productions. So that one you need to replace the big B and the big C. Okay, so you don't need to touch any other productions. Part B of that, the factor is a unit production. Everything else is fine. You just need to yank out a factor and put in what factor is, which is ID, num, open print expression, close print. Okay, left factor, I think pretty much everybody got that correct. Just looking for unique first token. If all of your production had a unique first token, you've left factored it. Okay, part B, for instance, for name is the common part. If you only did the for and not the name, then you end up with two rules that still don't have a unique token. Okay, so for name is the part you should factor out, and local is the one you should factor out. Okay, again, I don't think anybody had issue with the parse tree. I cover number 4. Number 5. So this one, there are two things. One is a program consists of a bunch of commands. Okay, program consists of a bunch of commands. So there's need to be some sort of a recursive rule there. Either that statement going to statement list concept, right? You can continue to repeat, or every single statement has to somehow repeat again. Otherwise, you only get one statement out of the entire program. Okay, so that's some sort of a recursive definition. So it gives you more than one command or one statement is what I'm looking for. The other part was that, okay, I'm enforcing, this has to be syntactically correct. And that's what we're doing with grammars, right? We want to be as precise as we can. Not all commands require 4 arguments. Some requires 3, some requires 2. Some commands don't have any arguments. Okay, so we don't want to lump them all to saying, okay, keyword arguments, 4 of them. Well, I could have a set C, which does not take a number at all, takes a color, a string in this case, or I could have a pixel only requires 2 numbers and not 4. Okay, so remember grammar, we're checking for syntax errors. Grammar says what's allowed and what's not, and what's allowed is, so you had to be a little bit more specific. So each single rule, line, number, 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 number. That's the rule. Okay, circle, number, 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 3 numbers. Pixel, number, number, 2 numbers. Okay, be very specific. And I only have 7 different commands, so it's not like it's going to be a long grammar, but you need to be a little bit more specific.
So would you do something like, you'd say like line and argument list 1, and then you would say
And
like
an argument
rectangle,
list.
argument list 1, which would be 4. So,
Sure,
and then circle is the argument list 2.
Yeah, that'd be
4, and
fine.
3.
Yeah, that'd be fine.
That's how they break it down.
Yeah, that'd be fine. Yeah, okay, that's one way to do it. Okay. All right, number 6. Defines, not defines, and then I throw in the if in there. We did talk about it in class with the if. As you can see here, the test is defined as 10. So that if test equals 5, that's not going to pass. Okay, with the pound ifs and what it defines is if it's not going to pass, it's not going to include anything in the if. Instead, it's going to include everything in the else. So at some point, what number let's see, we got pound define 1 to be 100, and then later pound define 1 to be just 1. Okay, so actually when you get through everything, when you get to x equals 1, the symbol is actually just the number 1. Okay, the 100 is gone. Remember, we can redefine, and that's on lab 1. If you have 2 pound defines, the very last one you saw, that's the one that overrode the previous one. Okay, so what's left in the code is void main, bracket, int x, because that's not wrap around any condition. You do not have x equals test, because that's part of the if, that's not true. But you do have x equals 1, which is the part of the else, that's the else. Okay, so x equals a number 1, not the letter, not the word 1, semicolon. That's what's left, 5 lines. Okay, so that's what I was looking for. In the symbol table also, the pound define file A underscore H, even though it has no value. And that's how you get around these multiple include file issues when you use the pound define. If it's in the symbol table, and I've seen it in this round, I'm not going to include that header file again. That's how we've always dealt with header files. And that's using the symbol table. And that's how it knows there's a file A underscore H. Right? If it's in the symbol table, if not in the symbol table, I put it in. The next time it will be in there, and then we'll bypass everything there, and I'm not even going to touch what's there, right? Okay, so, okay, so that's, again, if you have any specific questions, come and see me afterwards. But we're going to kind of move on. And okay, so I have issues with this thing. Sorry. It's, okay. All right. So homework 4. And after the break, I'm going to talk a little bit about project and then the lab 2, the second part. But I want to move on with this first and follow set. Okay, homework 4 deals with the LL1 parser, and I'm not having you do a lab this time. I'd like you to focus on the project instead of, because we did lose a couple weeks. And LL1, I think you'll like LL1 as a parser. I just don't think it's as useful as recursive descent or as useful as looking at some of the tools that will actually generate parsers for you later. Okay, so L1 is a top-down parser, and it's strictly one token look ahead. That means you must left factor everything, okay, in order to use L1. And what are the prerequisites for the grammar? No left recursion, just like recursive descent. Unit productions are okay if you can minimize it. Great, a little bit more efficient. Lambdas we can deal with. We have a way to deal with the lambdas, but must left factor to ensure that's one token look at. Okay, that's must. And how we do it is we compute what's called the first and the follow sets. So in the homework, I've given you 2 different grammars for you to compute the first and the follow set, and then the table. I've given you a table and said let's use it to parse something. I've also given you 4 different grammars and said, is this even LL1? Not all grammars are LL1. You have to do some work to make it LL1 if possible. Actually, having that one token look ahead makes it very difficult to make everything one token look ahead. And there are actually different varieties of LL. There are LL2, LLK. Okay, those are much harder to implement, much harder to compute. So the L, the first L is not, just means the input is coming from left to right. And next time, I meant to bring you a program language that actually reads from right to left, but I'll do that next time. I forgot to bring it. And the second L is the interesting. That's the top down. That's the leftmost derivation. When you grab a token, I'm going to take care of the leftmost symbol in my grammar and then move on to the next one. Okay, that's really top down. So that's why we don't have left recursions. If you have left recursion, you'll never be able to take care of that leftmost symbol. We'll just keep recursing and keep recursing and keep recursing. So that's the issue. So, and then we did very quickly, we only had an hour last week, so we did very quickly look at the first set, which is really just the first column. If there are no lambdas, first column. Okay, line them up. That's your first set. If it's a big letter, then go to the first set of that big letter. Right? If S starts with a big A, well, what's the first set of big A? Okay, move that into S. Right? That's how you compute the first set. Pretty easy if you don't have lambdas. When you have lambdas, you still circle that first column. That doesn't change. Okay, we did that last week, so I'm going to very quickly go through this. We still circle that first column. That hasn't changed. That doesn't change. What's different now is because that first column can go away because of the lambda, we also have to consider the second column for some rules. And maybe the third one, maybe the fourth one. We'll go in as steep as we have to until we get to a non-lambda rule, a token or symbol. That's when we stop. Okay, so in this case, the A could be lambda, so I have to consider big B as well. When I take the first set of something, like S could start with big A or big B, so I have to take their first set and move it into S. You never move lambda into S automatically, unless S itself could go to lambda. Okay, that's the only rule. You have to be careful with the first. Don't move the lambda. Just because A could go to lambda doesn't mean S could go to lambda. Okay? Unless both of them go to lambda. Then you have a lambda rule. Yes. Okay.
What happens when that lambda is S?
Okay, so notice S here. S could be big A, it's big A or big B, right? Big A followed by big B. Big A has a lambda, so it could drop out. The big B does not have a lambda, so it's going to have at least a D, E, or an E. So it's going to have at least this. So S itself does not go to lambda because B doesn't have a lambda, right? But if B were to have a lambda, then S could go to lambda if both of them drop out, right? Even though it didn't have a lambda rule to start with. So that's the only caution as you're looking at these rules. Okay, so the algorithm says if S goes to big A, I take big A's first set and copy into S, but don't copy the lambda. Okay, that's what the lambda says, minus the lambda. S could also start with big B because big A could drop out. Then I copy the big B's first set into S. Again, if there were any lambda, don't copy the lambda. Then look at S. Could the S itself go to lambda? That's where you put a lambda in. Okay, that's the only time you'll actually put a lambda in that wasn't there before. And how is that important? If S itself could go to lambda, that means that I don't need any tokens. I could just start with nothing, and that's okay, because S itself could go to lambda. But in this case, it cannot. It has at least an E. If nothing else, the smallest string I'm going to have is the E down here. I can have the DE, or I can have the AB, B, E, right? So there are different combinations I could look through, right? So
you're saying that if lambda was an SAB, then S would have to go.
yeah, S. Oh, notice S also has a little C, so S itself cannot go to lambda altogether, right? Yeah, that's what I'm saying. I think that's what you said. I said.
That if there is a lambda in the S production, A production, B production, then there can conceivably be
That could go to lambda, yes. Mm-hmm.
And then B would also have lambda, right?
Yeah, B would have to also have a lambda. And I may have a case coming up. I don't know. I have an example that shows that. Okay, not this one. This one, S does not go to lambda. You got S needs to have at least have a C. Okay, so on this one, oh, this is the one I wanted you to do. So this one I think we did last time. So A's first set is little a lambda. B's first set. Oh, you know what I'm gonna do? Oh, come on, really? What version of Word PowerPoint I'm using, but it's messing up my display. Sorry. Okay, so A's first set, remember this, that first column. A's first set is AM lambda. B's first set is B and lambda. Okay, and then S's first set is either, right, is big A, right, big A, big A, but because big A also goes to lambda, could go to lambda, I also have to consider the big B, and I also have to consider the C because both A and B could drop out, right? You see that? Let me put this back. Okay, now I'm gonna put a full screen so you can actually see, look, maybe. Okay, so A and B are pretty straightforward. I circle the first column, that's what I get, right? The S, however, if I circle the first column, I just get big A. And big A is just a little a. That's the first set minus a lambda. I don't move the lambda in there, right? I move the little a in there. But big A could drop out, so I also have to consider the big B, which has a little b as the first set. Okay, move that in there. But A, B could both drop out. Then I'll just end up with C as my first column. So therefore, S's first set is little a, b, or C. Okay, so this tells me how to, when I try to parse S, the only, well, in this case, I only have A, B's, and C's. I could have other tokens, it's not here. Okay, the only tokens that will work for S is A, B, or C. If somehow there was a D that got in there, well, that's not going to work. The only tokens I could use for S is A, B, and C as the first token, right? Because I can have other things. I can have A, B, and C, right? If each of them goes to one token each, okay? But that means if I have, any one of those tokens is my first token I'm looking at, right? Top-down parser is one token, one rule. So here I have one token, A. Which rule? Well, there's only one rule. It's okay. If I have one token B, yep, that rule works. If I have one token C, that same rule works. It just means I have to use a couple lambdas in there to make this parse tree work. If I have a D or any other letter, nope, it's not going to fit. Okay, so the first token tells me what rules will actually work here, right? And then sometimes if I have more than one rule, those tokens came from more than one rule, then I map them to the rule that they came from. Not this case. This case, they all came from that big A, big B, little c. Okay, but we are going to a little more complex. So we're going to move into more examples where you can see where that first set comes in and also how you can sort of map the rules. And that's where the table comes in, the LL1 table, which is really taking all of the grammar rules and put them into the table, mapping the actual tokens. Right? So I may have 5 different first sets tokens. I may have 3 rules. Well, which rule goes with which one? Okay, I'm almost always going to end up with more tokens than rules. Okay, so that means the rule is going to put in there more than once. Okay, but which column? Okay, how do they go in there? How do they map? And if I don't have, if I have more rules than tokens, then it's not LL1. I'm in trouble. I have more rules than tokens. That means one of those cells is going to get a little crowded. I'm going to put more than one rule to map a token. Then I don't have LL1. I need to left factor some more or something. Okay, it's not going to work. If I have lambdas, only if I have lambdas, I worry about a follow set. If I don't have lambdas, I don't worry about a follow set at all. Follow set is for tokens that should come after the symbol. Just take a look at this example. Okay, just take a look at this example. If A were to go to lambda, what should come after A? Obviously, if A were to go to lambda, that means I'm going to start out with either a B or a C. I did not start with A, right? So, but B and C's are okay. Because if A were to go to lambda, I could have a B after that, right, following the A. Or I could actually have the C because B itself could also drop out. That's how I compute the follow set. It's what's okay if A were to go to lambda. What token should I see? Obviously, I did not see an A. So A goes to lambda. Okay, that's fine. But what should I see, right? And in this case, because B could also go to lambda, well, if B were to go to lambda, what should I see? This case is pretty easy. You should see a C. If you didn't have a B, you should have a C. If you have anything else, then this thing doesn't parse, right? You should not have used the lambda there. That's what it means. If you see anything else than a C, then that B has issues. You should not go to lambda. B should map something else that you had there. Okay, so, and that's kind of the concept, right? The general idea. How to compute it, the follow set, takes a little bit of work because there are 4 cases. There are 4 cases. First 3 are easy. The fourth one is just a little hard to visualize what's happening, okay? So over the years, I try to draw parse trees. I try to have, the algorithm. If you follow the algorithm, it works, okay? But sometimes you just want to visualize the algorithm. Why does this work? Okay, that's a little harder. So if S is the start symbol, what should come after S? Well, nothing. S is done. When S is done, S is done. So that's always case 1. And we use, because this came from Unix, so we use a $ to denote end of something. So in this case, we use a $ to denote end of input. So what follows S? $. We may never, ever use that $. If S does not have a lambda, it may never use that $. But we're still going to put a $ in. And then case 2, this was the one where you have a little letter or a token following a non-terminal, a big letter, I call it. Then this one, big A, little b. So what should come after the big A? Well, little b. Okay, so put a little b in the follow set of big A. I don't care what's on the left-hand side. The left-hand side could be S, could be big B, could be A, doesn't matter, right? What I'm looking at, the pattern I'm looking at is I have a little letter following a big letter. So big B, the little b goes into the follow set of big A, okay? This is the easy one. Case 3, how about I have a big B following big A? Well, that's okay too. I know what big B's first set is, right? I line up that first column. I know what big B should start with. Okay, then take everything that big B should start with and put it in the follow set of A. Yes, we are going to look at examples, but this makes a little bit more sense. Again, there are no lambdas in a follow set at all. None. So when you take big B's first set, and copy it into the follow set of A, you don't copy the lambda. And there's just simply no lambdas in that follow set. And in fact, the follow set deals with the lambdas. What happens when you have lambdas? What token should you see? I'm not going to see a lambda token. There's no such thing as a lambda token. Lambda is nothing. So there's no lambdas in the follow set. Okay, That's case 3. I think we stopped there. We didn't really look at an example, which we are going to. We stopped there, but we're going to look at 4, case 4. Case 4, oh, by the way, case 3, and you can read the text if you like later. Case 3, we don't look at the left-hand side either. I got one big A, big B. That's what I'm looking at. That's the pattern I'm looking at. I don't care what the left-hand side is. This could be S going to big A. It doesn't matter. I'm looking at these two side by side on the right-hand side. Right? That's how I compute the first and the follow, right? That's how I compute the follow. Case 4, I do need to look at the left-hand side. Okay? Case 4, the pattern is I have a big letter at the end of a production. Okay? If it ends with a token, skip it. It doesn't fit. Right? But if I have a big letter all the way at the end of a production, what does that mean? What does that mean? Well, this is the real tricky one. What it means is, let's look at this. What follows big B? Well, if you just look at the right-hand side, it's like I'm at the end. It doesn't follow, it doesn't have anything after it, right? I'm all the way at the end of big B, so there's nothing after. It doesn't have a little letter, it doesn't have a big letter, nothing. But when you have A going to something B, this could be a unit production. This could have a bunch of other things in front of it, and then a big B, right? Doesn't matter. I'm just looking at all the way to the end, right? All the way to the end. So what should follow that B? Well, what should follow that B is whatever follows the A. Because A gets expanded into a subtree that has B at the very end. Very right hand, right? The rightmost node, right? So whatever this thing is that follows the A also follows the B. Because B is all the way at the end. So how do I use that? How do I use this knowledge? How do I use this algorithm? And over that. So what I like to do is you draw, right? You draw an arc so you remember, right? So I'm going to compute the follow set. I usually do is I'll start computing the follow set. I may have some big A's, S, doesn't matter what I have. Okay, I know the dollar sign always goes into the whatever my start symbol is, in this case S, okay? And then when I have case 4 like this, okay, A, derivation arrow all the way to B. Okay, that means whatever follows A also follows B because the derivation arrow. A going to all the way to B. So I actually mark it in my set. So I remember to copy it. So whatever is here, copy it down there. Okay, that's my algorithm. Whatever is there, copy it there. Don't forget. Why do I draw this? I won't forget. Why if I'm going through, I'm adding more things in here? Well, make sure it goes to B. Could B also go back to A? Well, could be. If I have another rule, how about this rule? Yeah, B can also go to A. There's no problem with circular. Okay, B can also go to A. There's no problem with circular follow sets. There's no such thing as circular follow set. That's fine. It's perfectly fine. Could A go to itself? Yes. This is the least interesting. A is already there. I don't have to copy into itself, right? So looking for these patterns, right? While you're looking for these patterns, so this one, S going to B, okay? Why B would go to lambda? and B drops out, then B is no longer the last symbol. Then S also gets to A, right? This is where lambda gets a little tricky. And you do have lambdas, otherwise we're not doing follow sets if you don't have lambdas. We have lambdas in there somewhere. When you're dealing with lambdas, when you're dealing with all of these cases, watch for the lambdas. The B's could drop out. S then will also could just go to A without a B. So you gotta, I always draw my arrows. I remember to copy them all in. We already saw this case. C follows the B, but if B was to drop out, then C also follows the A. Okay. How about this case? Some of these could be lambdas. This is one pair. First of B follows the A. This is another pair. First of C follows the B. Or what if B were to drop out? Then you can also have this. First of C follows the A. So all of a sudden you have all these different permutations of different things happening to your follow set, right? There are tools out there to do this. Not very good tools, but there are tools out there to do this. One of the project options is, can you do this programmatically rather than enter all these algorithms into your program? Here's a grammar. Go figure out the first and follow set. Go construct this table automatically. Right? It's a lot of work if you do it by hand. Okay, so let's look at some examples. Okay, so all of my examples so far are case by case, right? And I apologize, the reds don't show up, but it's case by case. Case one, every single follow set, case one, starts the same way. Put a $sign in the star symbol. Okay, I did that. Case two. Okay, this one doesn't have lambda actually, so I really don't need the follow set, but I want to illustrate anyway how the algorithm works. The little c follows the big B. Little c follows the big B. The big B doesn't drop out. There's no lambda. So little c is in the B's follow set. Little c follows the B. That's how you read this. Right? $sign follows S because when you're done, you're done. Low C follows B because that's the case two that was given. Case three, big A, big B. So B follows A. Well, what could B be? B is D and E. So D follows big A, E follows big A, and that's exactly what I put down. All right, so what follows A is the first of B minus the lambda, first of B, and first of B, my circle in the first column is D and E. Okay, so they go in there. All right. Again, okay, those are the easy ones. Case four. Okay. And I do draw, and I do mean draw them, otherwise you will not remember and you don't get them in correctly. So I'm looking for pattern 4. Big letter at the end. Not the first one, not the second one. The third one, big A, something, something B. Okay, so everything that follows A also follows B. So write it down. Draw it, write it down. Okay, A goes B, yep, a little token, that doesn't apply. Big B, going to big B, okay, it's already there. So I don't have to write anything else. So what gets copied down is everything from A now gets copied into B's follow set. Okay. And the last production is fine. All right. So the 4 cases. Let's do another one. phone. My phone is in another room. Okay. Case 1. Oh, okay, this one does have lambda, so we do need the follow set this time. S follow set, $sign, case 1. Case 2, I had a BC again. Okay, so little c follows big B, put it in. Little c follows big B, but B could be a lambda. So B could drop out in the middle. Then I'll have the C following A. Okay, put that in. C follows the A. Case 3, same thing. As we saw earlier, big B, big A, big B. So B's first set is B or lambda, right? But you don't copy the lambda in, so you just copy the B in. So B gets added to the follow set of A. In this case, I don't have any case 4. There's no big letter at the end of any production. So that's it. There's my follow set. And I go into, okay. So what have you doing? We actually did this one last time. We did the first set last time. So I'm going to give you the first set. So you have the computer first set again. And this is also probably a good time to take a break. So if you like, take a break and then come back and work on the follow set of this one, and then we'll talk about it. This one also has case 1, 2, and 3, and now case 4. Okay, there's no big letter at the end of any production. So just case 1, 2, and 3. Let's do this one, and then we'll do one with case 4 and see how we copy things over. And then I think I have a few more examples for you to do. Let me turn off Hangout. Up again. I just need to turn off Hangout. And I do want to save it, yes.